All right, so the intermolecular forces are additional attraction forces. As I mentioned, you already have the molecule. The molecule already formed. How you link the molecules together? You link the molecules together through the intermolecular forces. We have 4 different types of intermolecular forces. The first type is ion dipole. And I explained to you before, when you hear the word ion, that means you have an ionic compound. Dipole means you have a polar covalent molecule. So this is an interaction between an ionic molecule and a polar covalent molecule. Then we have the van der Waals forces, which is these 3 types of forces. And the first type is dipole-dipole forces, which is again between polar molecule and a polar molecule. London dispersion forces between non-polar molecule and non-polar molecule. And then we have hydrogen bond, which is a specific bond that has hydrogen as a focus of that particular bond. So we're gonna talk about all of these intermolecular forces again today. So the first type of intermolecular forces is ion dipole forces. Ion dipole, it coming from its name. You have an ionic molecule. That ionic molecule will produce ions, negative and positive. That negative is anion, that positive is cation. And you have a polar molecule. Where polar molecule will come from? From the covalent molecule. Dipole moment doesn't cancel each other. If it doesn't cancel each other, you have a polar molecule. If the dipole moment cancel each other, you have a non-polar molecule. So to identify a molecule polar or non-polar, you will have to draw the molecular geometry and identify the dipole moment and see if they enhance each other or they cancel each other. If they cancel each other, then this is non-polar molecule. If they enhance each other, that's a polar molecule. So polar molecule will have partial positive, partial negative. How the interaction is going to take place? The interaction is going to take place between the ions, the negative ions, and the partial positive in the polar molecule. So you can see right now the negative will be attracted by the partial positive. On the other hand, the positive ion will be attracted by the partial negative. And that will create the ion dipole. And this is how solid dissolve in water. So if you look at sodium chloride, how sodium chloride dissolve in water? Sodium chloride dissolve in water by this intermolecular forces, which is ion dipole. The sodium ion will be surrounded by oxygen, which carry the partial negative, as you can see here on the right-hand side of this image. While the chlorine, the chloride negative, will be surrounded by the hydrogen, which is the partial positive. And you can see here that will be the ion dipole interaction. So the ion dipole interaction, again, will basically an interaction between negative and partial positive and positive and partial negative. Where the partial come from? From the polar molecule. Where the positive and negative come from? From the ion. So what will be the name of the intermolecular forces? Ion dipole. So from the name, you will be able to determine which molecule interacting with each other. Since this is an ion dipole, this interaction will depend on the strengths. This interaction here between the positive and the partial negative will depend on the positive. The higher the charges, the higher the interaction. So if this is positive 2 or positive 3, if this is a different positive, if this is magnesium or aluminum, then you're going to have a stronger interaction. Why are you going to have stronger interaction? Because the higher the positive, the higher the electrostatic attraction forces. The electrostatic attraction forces depend on the charges. The higher the charges, the higher the interaction. What other factors reflect on the attraction forces? The distance. The distance between these 2 atoms here, the cation and the partial negative here, which is oxygen. The smaller the distance, the higher the interaction. So the smaller the distance, the higher the interaction. How the distance can be smaller? The size. The smaller the size of the positive, the higher the interaction. So we have two different factors affecting the ion-dipole interaction. Factor number one is the charge. The higher the charges, the higher the interaction between the cations and the water. Factor number two, the size. The smaller the cation or the smaller the positive, the higher the interaction. Okay, so the smaller the ions, so here's what I just mentioned. The smaller the ions, the higher the ion-dipole interaction. Lithium ion will have stronger interaction with water than sodium ion. Why lithium will have a higher interaction than sodium? Going back to the predictor, here is lithium and here is sodium. Lithium is higher up, then will be smaller in size. So lithium will be smaller in size, will have a stronger interaction with water. Factor number one, the smaller the ions, the higher the ion-dipole interactions. So if you're comparing lithium positive and sodium positive, remember both of them has positive. So the charge is the same. So there's no factor here related to the charge. What's factor affecting these two? The size. Which one is smaller in size? Lithium. So lithium positive will be smaller in size, mean stronger interaction. Now, if you have positive 3 versus positive 2, which one will have a higher interaction? The positive 3 or the positive 2? And the answer is positive 3 will have a higher interaction with water. All right. So to just recap this one more time, the ion dipole, it's an interaction between an ionic molecule and a polar covalent molecule. The ionic molecule is clear. We identify what's ionic molecule between metal and non-metal. The polar molecule is identified by the dipole moment, and as I showed you earlier. And there are two factors affecting this interaction. Factor number one is the size. Factor number two is the charge. The smaller the size, the higher the electrostatic attraction. The higher the charges, the higher the electrostatic attraction. So these are the two factors that will reflect on the ion dipole strengths. All right. Now, if we don't have an ion system, so if you don't have an ionic system, now you have a polar system. If you have a polar system, then you have dipole-dipole. You don't have ions anymore. You have dipole-dipole. So this dipole-dipole, which means partial positive, partial negative, you're going to have the partial positive of one of the molecule connecting to the partial negative of the other molecule through this intermolecular force. Remember, the intermolecular forces are dot lines. These dot lines here represent the intermolecular forces. The solid lines represent the molecule itself. So here is an example. So this is an example of dipole-dipole interaction. Here is HCl. So this is HCl. Here is another HCl. These two molecules will be connected to each other by the partial positive from the hydrogen of that molecule to the partial negative of the other molecule. And that will create the intermolecular forces, dipole-dipole. This is a solid line. The solid line is the covalent bond. Remember, the covalent bond is going to be the solid line. The dot line here is the intermolecular forces, which is in this case the dipole-dipole. Here is another example, HI. So HI can connect to another HI, can connect to another HI. You can see it's a chain linking all the molecules together. So the intermolecular force is a continuous chain. That continuous chain is linking all the molecules together. And if you can link all the molecules together, you can have chances that the molecule can be in liquid phase or solid phase. If the molecules are not connected to each other, they cannot be in liquid or solid, because if there is no interaction between the molecules, then the molecule will be in the gas phase. The gas has no intermolecular forces between them, cluster, the molecule gather and interact with each other through the dipole-dipole interaction. Since we are talking about the dipole-dipole interaction, we're talking about the dipole moment. The dipole moment is going to be an important factor here. The more polar the molecule, the stronger the interaction. The more polarized the molecule, the stronger the interaction. The higher dipole moment, the stronger the interaction. Because these forces depend on the dipole moment. The higher the dipole moment, the higher the interaction between these molecules. So here is an example showing that. These are three different substances. These three different substances has pretty much similar molecular weight. And why you're keeping molecular weight almost the same? Because remember, you cannot compare water to butter. Butter is very high molar mass. Butter is solid at room temperature. Water is liquid. Why it's unfair to compare water to butter? Because water has 18 grams per mole. Water has a molar mass 18 grams per mole. Butter has almost 300 grams per mole. So you're comparing an 18 grams per mole to 300 grams per mole. It's just unfair. So in order to compare the dipole moment, you have to make sure the molar mass is almost the same. So that's why we're keeping that column almost the same. 44, 46, 41, they're plus or minus 5. They're not plus or minus 100, right? So we're keeping them within that range, which is basically because the molar mass will affect the shape. All right, so the dipole moment is what we're studying here. We're studying the effect of the dipole moment. So the dipole moment in propane is 0.08 because it's non-polar. This is carbon-hydrogen. Carbon-hydrogen are non-polar molecules. You can see their dipole moment is very, very low. Methyl ether is 1.3. Acetonitrile, 3.93. You don't have to memorize the names. I'm not going to ask you about the names. I'm going to ask you about these values. What these values represent? These values represent how polarized the molecule. The higher the dipole moment, the higher the polarization. So which one of these is more polar? Acetonitrile, CH3CN. So this acetonitrile will have the highest boiling point. Look what happens. A stronger molecule will have a higher boiling point. A weaker molecule will have a lower boiling point. Because remember what the boiling point is. Breaking the intermolecular forces between the liquid, converting it to gas. If you can convert the liquid to gas very easily, that means it has very weak intermolecular forces. But if you need to heat to a higher temperature, that means the intermolecular forces is stronger because you need to heat to a higher temperature. So which of these is the weakest system? The first one. It boils at 231 Kelvin. Which one is the stronger system here? The last one, the acetonitrile, boil at 355. So the higher the boiling point, the stronger the intermolecular forces, the stronger the system. So as the dipole moment increases, the intermolecular forces increases. As the intermolecular forces increases, the boiling point increases. So this is the outcome, or this is basically the conclusion of this table here. Increase the dipole moment, you increase the strength of the intermolecular forces. You increase the strength of the intermolecular forces, you increase the boiling point of the molecule. Okay, how about if we have non-polar? So far we talked about the polar. We talked about the ion dipole. So we talked about the ionic system and the polar system, which is these two are very polarized. Now, how about if we have non-polar system? A non-polar system means there is no dipole moment because the dipole moment cancel each other. So like hydrocarbons, all hydrocarbons are non-polar. So what will be the type of forces that gather this molecule together? And that intermolecular forces is known as London dispersion forces. So this is the forces between the non-polar molecule. If you identify a molecule to be non-polar, then the type of forces exist will be London dispersion forces. What will be the intermolecular forces between the carbon dioxide molecules? The intermolecular forces would be London dispersion forces. Why? Because it's non-polar. How do I identify this to be non-polar? The dipole moment are canceling each other. What will be the intermolecular forces between carbon tetrachloride? The intermolecular forces is going to be London dispersion forces because, again, they cancel each other and the dipole moment is zero. So once you identify a molecule to be non-polar, they have only one type of forces, which is London dispersion. And these very weak forces are very short in range and attraction. So that's why noble gas has very, very low boiling point. So how the noble gas interact with each other? They interact through the electrons of one atom interacting with the nucleus of another atom. So this is how the London dispersion force is. It's an electron from one atom attracted by a nucleus in another atom. Why it's a short range? It's a short range because these electrons are rotating around the nucleus. These electrons are in motion. You don't have a continuous interaction. You have an instantaneous. The word instantaneous versus continuous, the instantaneous mean at that moment, at this moment in time. Continuous mean this is continuously interacting with this, which is not true. This is an instantaneous because of this incident of this particular moment in time. These electrons are attracted by this nucleus and creating that London dispersion forces. So the London dispersion forces are weak forces because they are not continuous forces. There are short range attraction forces and they happen instantaneously between the electrons of one atom with the nucleus of one atom. So what factor can affect the London dispersion forces? If you recall what I just mentioned about water versus butter. Butter at home that we use for cooking is hydrocarbon, which is London dispersion forces. But why butter exists as solid? If something that is that weak, how can it exist as solid? And the answer is very simple, because of the molar mass. A high molar mass will make the substance exist as solid. But look at butter. When you put butter on the stove, think about what happened. You put butter on the stove, about 10 seconds and the butter is melted. What does this mean? It tells you that this has very weak intermolecular forces. If something melts within 10 seconds when you put it on the stove, that indicates that this system is weak. But still exist as solid. Why exist as solid? It's okay to exist as solid. Not necessarily because it's solid, that means it cannot be melted in seconds. Because when you say the word solid, that will be relatively comparing different systems to each other. So when you compare a butter versus iron, if you compare butter versus iron is very strong system, butter is very weak system. Both of them are solid. Can you melt iron in 10 seconds in the stove as you're melting the butter? No. Why? Because butter is London dispersion forces. And London dispersion forces are very weak intermolecular forces. So the molar mass. So factor number one is the molar mass. The higher the molar mass, the higher London dispersion forces. If you're comparing two non-polar systems, which system will have the higher London dispersion forces? The system that has the higher mass. So if you're comparing two systems, this two system has London dispersion force only, then the higher the molar mass, the higher London dispersion forces. The second is the shape. How about if both of them has the same mass? If both of them has the same mass, how can I define which one has a stronger interaction? That would be the geometry of the molecule. The more linear the molecule, the higher the interaction. Why you want the molecule to be more linear? Because it's an atom-to-atom interaction. And you want this interaction between all the atoms. If the system is linear, you have more interaction than a crowded system. In a crowded system, you cannot only interact the outside atoms, not the inside. So here's an example. So this is a linear, this on the left-hand side, this is a linear, you can see the carbon atom in a linear interaction here. So these two molecules right now can interact with each other. They can see each other, as you can see here clearly, all this atom can interact with each other. Look at this atom here, crowded. So you only see this atom here can interact with this atom. So only two atoms from each molecule here can interact with each other, while this one here, you have all the atoms can interact with each other. So this is clearly because it's crowded, and as the molecule is crowded, it becomes difficult for all the atoms to interact with each other. And look what happened to the boiling point. The boiling point for N-pentane, which is this one here, is 309. The boiling point for the new pentane, which is a crowded system here, is 282. You can see clearly both of them has exactly the same mass. They're exactly the same number of carbon atom, the same number of hydrogen atom. So they're exactly the same, except the geometry. One is linear and one is branch. The linear has a higher boiling point, and the reason for that because it has more interaction. So this is again, so we have two factors affecting London dispersion forces. Factor number one, which is very easy, the size. As you increase the size or the molar mass, the intermolecular forces increases. The second is the geometry. The more linear the geometry, the stronger the interaction. The carbon hydrogen written in the model here. And this is the, look at the crowded one. Look at the crowded, how the atoms are so crowded. Now, the last type of intermolecular forces comes to its name, which is hydrogen bonding. So hydrogen bonding is a dipole-dipole interaction. It's this type of interaction. So hydrogen bonding is dipole-dipole interaction. But why we did not call it a dipole-dipole? Why we call it a hydrogen bonding? Because first of all, is much stronger than a dipole-dipole. The hydrogen bonding are much stronger bond than the dipole-dipole. What makes this much stronger? Because it has a specific atom, which is hydrogen atom, connected to the specific atoms, oxygen, nitrogen, and fluorine. So if you have a hydrogen connected to oxygen or nitrogen or fluorine, your interaction is hydrogen bonding. So to have a hydrogen bonding, you need hydrogen connected to oxygen, or hydrogen connected to nitrogen, or hydrogen connected to fluorine. This is how you identify that you have a hydrogen bonding. Otherwise, you have just dipole-dipole interaction. So HCl, if I go back to this, why HCl we did not call it a hydrogen bonding? Because chlorine is not one of these atoms. It's oxygen, nitrogen, or fluorine. Why HI, we did not call it a hydrogen bonding? Because again, you don't have these three unique atoms. And these three unique atoms are nitrogen, oxygen, and fluorine. So here is the water. Water is a very unique system. Why the water is a very unique system? Because water can make two hydrogen bonding per molecule. So the oxygen can polarize these two hydrogen to make a hydrogen bond with other oxygen in a different water molecules. And you get this, again, chain linking water molecules together. And this is a very strong interaction. And that's why water boil at 100 degrees Celsius. Water boil at a very high temperature compared to its molar mass. The molar mass of water is 18 gram per mole. This is very, very small. Yet water boil at 100 degrees Celsius. 18 gram per mole boiling at 100 degrees Celsius. If water doesn't have its hydrogen bond, water will be boiling at -70 degrees Celsius. If water does not have a hydrogen bonding, I will repeat this again, water will be boiling at a very low temperature in relationship to the molecular mass. All right, so this is the hydrogen bonding here happening between the hydrogen connected to oxygen with another oxygen. So clearly, to have a hydrogen bonding, you need hydrogen connected to oxygen, nitrogen and fluorine, and it has to make a hydrogen bonding with oxygen, nitrogen, and fluorine. So clearly, you always have to have a hydrogen bond involving these atoms: hydrogen, oxygen, nitrogen, and fluorine. And since you have these atoms, we have two different types of, again, nomenclature here. The first one is the hydrogen bond donor. How we identify the hydrogen bond donor? The hydrogen bond donor is the atom that is connected directly to hydrogen, which will be oxygen, nitrogen, or fluorine. So the atom that is connected through the covalent bond, that will be hydrogen bond donor. The hydrogen bond acceptor is the atom that's accepting the hydrogen bond. And this is not necessarily has to be connected to hydrogen. This one can be oxygen, nitrogen, or fluorine. So you can see the difference between these two. This is accepting the hydrogen bond, is not necessarily connected to hydrogen. It has to be oxygen, nitrogen, or fluorine. This one here is the one donating the hydrogen bond. Why it's donating the hydrogen bond? Because it's connecting to the hydrogen. Water compared to all of these, look, all of these, water compared to all of these molecules. Water is the highest boiling point out of all these molecules. And why is that? Because of the hydrogen bonding. After that comes HF. Why HF is lower in boiling point than water? Because water can have 2 hydrogen bonding per molecule. Water can do 2 hydrogen bonding per molecule, while HF can only do 1 hydrogen bonding. So water can only do 1 hydrogen bonding per molecule because you can see it's only 1 H. Water can do 2 hydrogen bonding per molecule. Okay. So another very important intermolecular forces is, again, the hydrogen bonding is responsible of linking the different nucleobases of DNA, as you can see here, and making this helica shape. This helica shape is made by the hydrogen bonding, and if you look at that, where is the hydrogen bond? Between the oxygen and the hydrogen connected to the nitrogen. Which one is the hydrogen bond donor? This one here is the hydrogen bond donor. Which one is the hydrogen bond acceptor? The oxygen here. So again, how do I know, one more time, how to identify the donor and the acceptor? By looking at who's giving the hydrogen bond. This oxygen here. Why? Because it's the one connected to hydrogen. Who's accepting the hydrogen bond? This oxygen here. So hydrogen bond acceptor, hydrogen bond donor. The hydrogen bond donor is the one directly connected to the hydrogen. This is the hydrogen bond donor. This is the hydrogen bond acceptor. This is the hydrogen bond acceptor. Why this is acceptor? Doesn't have hydrogen. This is the hydrogen bond donor. This is the hydrogen bond donor. This is the hydrogen bond acceptor. So to finalize this part, how can we identify the intermolecular forces in a given molecule? So when you look at any given molecule, you will see where the interaction sites are. What are the interaction sites in alcohol? We have 2 interaction sites. Number 1, carbon connected to oxygen. This will create a dipole moment, partial positive, partial negative. So we have a dipole-dipole interaction site. Do we have a hydrogen connected to oxygen? Yes, that will create a hydrogen bonding site. Do we have London dispersion forces? Yes, all molecules will have London dispersion forces. So what is the type of intermolecular forces in alcohol? Number 1, dipole-dipole, hydrogen bonding, and London dispersion forces. Which one responsible for the properties of alcohol? Hydrogen bonding. The most strongest intermolecular forces are the one that is going to control the effect or the strength of the molecule. Now let's look at dimethyl ether. This one here, dimethyl ether. Do we have hydrogen connected to oxygen? No. So this one doesn't have a hydrogen bond. You have to have a hydrogen connected to these 3 atoms. So do we have a hydrogen connected to oxygen? No. So there's no hydrogen bond. What do we have here? Dipole-dipole interaction. Partial negative, partial positive. This is partial negative, partial positive, partial negative, partial positive, and they don't cancel each other. Why they don't cancel each other? Because this is a bent structure. This is not a linear. This is a bent structure. So what will be the intermolecular forces that's affecting this structure? Dipole-dipole. Remember, we have Lambda dispersion in all of them. But this one has a dipole-dipole is the one affecting this molecule. Now, the last one here, do we have hydrogen connected to oxygen? No, there is no oxygen here. So this will be non-polar. This is non-polar. If this is non-polar, it has only Lambda dispersion forces. So comparing these three, which one is the strongest system? Which of these three molecules is the strongest system? Will be the one on the left-hand side, the alcohol. Why the alcohol are stronger? Because alcohol has dipole-dipole and it has hydrogen bonding. This one has only dipole-dipole. So where is the order of the strengths? The ion dipole come first, followed by hydrogen bond, followed by dipole-dipole, and the weakest is Lambda dispersion forces. So the strongest interaction is the ion dipole, followed by the hydrogen bond, followed by the dipole-dipole, and then the weakest is the Lambda dispersion forces.